In this video, we'll be taking a closer look at some of the methods of proof that we've looked at in previous videos, trying to organize things a little bit. So we're going to begin with a little bit of notation, some of which we've seen before, the first two items in particular. So if capital A is a set of objects, say the set of integers, and x is an object, then this sequence of symbols, x and what looks like a Greek epsilon, a, is shorthand for x is one of the objects in the set A. Or for short, x is in A. Or we frequently say x is an element of A. This looks like a Greek epsilon, but it's actually typeset slightly differently. And then if x is not one of the objects in A, we put a slice through the is an element of symbol to negate it. So, for example, 51 is an element of the set of integers because 51 is an integer, and 3/7 is not an element of the set of integers. 3/7 is not an integer. And now some notation that we haven't seen before, at least on the slides. This sequence of symbols, this thing that looks like an upside down capital A, x is an element of A, is short for the phrase for every x in A. In other words, the capital upside down A is a shorthand for every, or sometimes for all, or some equivalent phrase. And then this backwards capital E is shorthand for the phrase there exists or there is. So this sequence of four symbols would be read, there is an element x in A, meaning there is at least one. So for example, here is a mathematical sentence using the for all abbreviation. If this were read, filling in the words for the abbreviations, this is read for every integer x. X is a divisor of x. Or sometimes, as I said, we use the phrase for every integer x. X is a divisor of x. Okay, now we look at the proof principles, which I've sort of organized into four principles. The first is proving a for all statement. So this probably makes more sense when you're looking at a specific example, and we will shortly. But the principle is if capital A is a set and P of x is a sentence in which the variable x occurs, and you want to prove the mathematical statement for all x in A, P of x. In other words, we're proving for every x in A, the sentence P of x is true. The way to do this is sort of the natural thing you might do. You assume that x is an element of A, an arbitrary element, and using only that fact about x, you try to prove that the sentence P of x is true. So here's an example. Something we saw previously. We were proving for all integers a, b, and c If A divides B and B divides C, then A divides C. So we're proving for all integers A, B, and C that something happens. We would start by assuming that A, B, and C are integers. So we assume we have three arbitrary integers, A, B, and C. And now how can we argue for the statement following the for all? How can we argue what we have to prove is, in other words, that if A divides B and B divides C, then A divides C. And you do this by just simply writing assume A, B, and C are integers. This would be the first line of your proof. And then with this assumption, as I said, it would be our job to prove the if-then statement. So, few more details. When you write the line assume A, B, and C are integers, then the symbols A, B, and C for the rest of the proof represent fixed arbitrary integers. And you can use those symbols and the fact that they are integers in anything else you have to do in the proof. For example, you might have to construct another integer of a certain type. What do we know about A, B, and C? These arbitrary fixed integers. We know they're integers, and that's it. That's all you can use. Although later assumptions in the proof might give you more facts about A, B, and C. There is a diagram which is supposed to illustrate in graphic form how this principle works. May or may not be helpful. So what I have are two rectangles, one representing the situation before you use this first principle. So we want to prove, the idea is we would like to prove that for every x in the set capital A, P of x, right, the last line of our proof will be hence or therefore for all x in A, P of x. And we want to fill in the proof. Well, using the principle that we just talked about, you can do some filling in. After using the principle, you would begin the filling in by assuming x is in A, and based on that assumption, proving P of x. Of course, there will still be a gap here, but we have succeeded in narrowing the gap between what we know and what we want to prove. So in this inner box, you know, after saying assume x is an element of A, that x is a arbitrary fixed element of A which you can use. Principle number 2, if you want to prove an if-then, say the implication if Q then R. The way to do it is assume Q is true, and using the assumption that Q is true, you have to give a proof that R is true. As we did in our examples in previous modules, you assume Q is true by writing the line assume Q. And by doing that, you are adding Q to the things you can use. The things you can use to prove R. So going back to the example we were just looking at, after assuming that a, b, and c were integers, we had to prove the if-then statement, the implication. If a divides b and b divides c, then a divides c. According to principle 2, you do what we did when we did this proof earlier. You assume Q is true. In other words, you assume A divides B and B divides C. And then using this assumption, you have to prove the conclusion of the if-then. You have to prove R, which in this case is A divides C. And here's the before and after diagrams, which again you may or may not find helpful. So the first rectangle represents the situation where you want to prove if P then Q. You're hoping for a last line, hence if P then Q. And you've got to fill in the proof. One way to fill in is to use this proof principle, and after you use it, here's what the situation would be. You have assumed P. There will still be some proof to be filled in. It should be a proof of Q, and once that's completed, you will have your proof of if P then Q. So these two proof principles are frequently used together. In fact, I think statements beginning with a for all followed by an if then occur more frequently than any other kind of statement that you will be proving in mathematics. So I've combined those two principles into a third principle. Frequently they're used together like this. So if you want to prove for all integers a, b, and c, the if-then statement, if a divides b and b divides c, then a divides c, you assume a, b, and c are integers, and you assume a divides b and b divides c, combining the two things that we did earlier into one step. To prove for every x in A, if Q of x, then R of x. Here we are in a more abstract setting. Since we're proving a for all x in A, you assume x is in A. And since we're proving if Q of x, then R of x, you also assume Q of x. And based on those two assumptions, you need to give a proof of R of x. Here are the before and after diagrams. Before, we are hoping to prove for all x in A if Q of x then R of x. After using this principle, we have added what's in the inner box. Assume x is in A and Q of x. There will still be a gap here most of the time, and once you've proved R of x, you will have succeeded in proving for all x in A if Q of x then R of x. Here's one thing you've got to be aware of when you're proving a for all statement followed by an if then. This turns out to be sort of a minor point in most circumstances. In these kinds of statements, for all followed by an if then, mathematicians have the habit of leaving off the words for all. So, for example, the example sentence that we've been looking at, for all integers a, b, and c, if a divides b and b divides c, then a divides c. would frequently be stated like this. If a, b, and c are integers, and a divides b and b divides c, then a divides c. It isn't, in this second version, it isn't really being made explicit that we mean for all integers a, b, and c, but most people would interpret this as meaning for all integers a, b, and c. And if that's the way you interpreted it, you interpreted it correctly. Okay, the fourth of the four proof principles, proving that two things are equal. There are several ways to do this, which I mention in this paragraph. Probably the most frequent method of proving an equality is to start with one side and apply legal operations and get the other side. But sometimes that doesn't work out extremely well, and you can start with one side, say the left-hand side, which is A, do legal algebra and get some expression, say C, and then take the other side, which is B in this case, and get the same expression C. And you, if you've done that, you will have proved that A and B are equal. And then a third possibility, which occurs less often, is to start with an equality you know is true and perform legal operations on that equality using the things you know to end up with the equality you want to prove. So all this is probably more understandable with examples. So here is one example. Let's suppose we want to prove for every real number r, real number little r, if r is not equal to -1, then this equality holds. So let's begin the proof. And since it is a for all followed by an if then, and even if you didn't know the third proof principle, this is what you would probably do. You would assume you've got a real number r, and that it's different from 1, and you would try to give an argument for the conclusion of the if then. In other words, for this equality. And that's what I'm going to do. I'm going to start with the left-hand side and do algebra and try to obtain the right-hand side. And the algebra that I'm going to do is just what you might do in an elementary algebra course. So we're going to add these two numbers by first writing r to the n as a fraction with r minus 1 as its denominator, so that we can do the addition of fractions. So we're thinking of r to the n as being r to the n over 1, and we're multiplying the numerator and denominator by the quantity r minus 1. And now we're adding two fractions with the same denominator. So you add the numerators, and the answer has as its denominator the common denominator. And now I'm going to multiply through in the numerator by this r to the n, resulting in r to the n minus 1 plus r raised to the power n plus 1 minus r to the n. All that divided by r minus 1. And now combining the r to the n and the minus r to the n leaves me with r raised to the power n minus 1 minus 1 in the numerator and r minus 1 in the denominator. And that is the right-hand side of the equation I want to prove. I have finished the proof, and here our little square is the end of proof symbol. Okay, here is a summary of the principles that I just talked about, just to have them all in one place. And now for the remainder of the video, I want to talk a little bit about style when you're writing a proof. These are sort of the accepted conventions that are expected when you're trying to write down a mathematical argument. So, first of all, the standard way to order statements in a proof is to start with what you know, the hypotheses, and end with what you want to prove. It's what I've called the conclusion here, with every line of the proof following from previous lines. So the standard way of doing this is to have the lines in logical order. Each line follows from lines above. There are alternatives to doing this, but you have to be a little careful when you use them. So, for example, in our proofs so far, and this is what I usually try to do, after writing down my assumptions, I write down what I have to prove to keep myself on track, and I think it makes it easier for other people to read the proof. But when you do that, you have to make sure that it's clear that what you've written down is something that you still have to prove, which you could do by preceding it with the phrase, "we have to prove." Okay, second guideline. It is a good idea to give some indication of the reason for each sentence in your proof. If it's an assumption, that should be clear. You could begin it with the word assume. If it follows from previous lines, then using words like therefore or hence are helpful to alert the reader that this sentence in the proof is following from previous lines. And it's sort of a convention. If a line of a proof follows from the line right before it, then the word then is frequently used. If a sentence follows from a line other than the one immediately preceding it, it is a good idea to refer to the line from which it follows. And if a mathematical sentence like an equation appears in your proof and you don't say why it's there, there are no words therefore or this follows from something, the reader of the proof will usually assume that what you've written down follows from the previous line. These 4 bullet points didn't quite all make it onto the slide, but almost. Okay, another style guideline. When you use an assumption, one of your assumptions from the beginning of the proof, when you use that assumption, it's good to explicitly mention it. I say it should be explicitly mentioned. These though are guidelines, not absolute rules. This is not necessary if it follows from if the assumption from which it follows is the immediately preceding line. So this will be easier if your assumptions are numbered, or if you number the ones that you know you are going to have to use later in the proof. So as an example, here's an out-of-context line from a proof. So somewhere in your proof, you might assume that x is a real number and x is between -1 and 1. And I have numbered that assumption with a number in parentheses. That's the usual way of doing things. And then later in the proof, if you use this assumption, you can refer to the assumption by number rather than having to rewrite the whole thing or part of it. So, for example, this might occur later in the proof. By sentence number 1, we conclude that the absolute value of x is less than -1. So these are just two sentences out of context. And then here's something I mentioned earlier. Whenever a sentence describes something that still has to be proved, like the thing you're trying to show, you really need to indicate that fact. Otherwise, it's likely to be confusing. So, as I said before, you can use a phrase like "we will show that," or "it suffices to prove," or our goal is to show, something along those lines. And let me just mention that it is not a valid method of proof to begin with what you want to prove. Like if you want to argue for an equation, it's not valid to begin with that equation and from the equation derive something known to be true. So this is doing this is a bad habit that's easy to get into, so I just want you to be aware of it. You shouldn't start with what you want to prove and end your proof with what you know, especially if there's no indication of how the lines of the proof are related. So here again, for an example, I'm going back to the theorem I proved earlier, and I'm going to give you what I consider to be an incorrect proof. Okay, so we're starting the proof by assuming little r is a real number and little r is not equal to 1. This is okay. This is how we began before. Okay, and now looking at this equality, I've written it down here, or reproduced it, and now I'm going to work with this equality. I'm going to begin by multiplying both sides by r minus 1. This is a typical algebraic thing to do. To simplify an equation, you clear it of fractions. Okay, if you multiply by r minus 1, on the left-hand side, for the first term, the r minus 1's cancel, and for the second term, without doing any simplifying, you get quantity r minus 1 times r to the n. And on the right-hand side, the r minus 1's cancel. And then multiplying through by r to the n on the left-hand side gives us this equation. And on the left-hand side, combining the plus r to the n and the minus r to the n gives me this equation. And this is true. And so the proof is done. But this proof is incorrect. We've made the mistake of starting with what we want to prove and deriving something true. Not a valid method of proof. Okay, a few other things. a proof should consist in complete sentences. You're writing something that somebody else has to read, and when it's read out loud, it should sound like ordinary English. But you can use mathematical abbreviations, but when a person reads those out loud, they are translated into English. And one thing in particular that you should be careful of is leaving out equality signs. If you want to say two things are equal, then you have to put the equality sign in to make the thing into a mathematical sentence. Here's sort of a silly example. So here's something that's not really a proof, because it doesn't make complete sense because the equality signs are missing. What I'm attempting to prove is that x minus 1 quantity cubed is equal to, well, we'll see at the end. So basically I'm just going to multiply out. So this is not a proof that x minus 1 quantity cubed is x cubed minus 3x plus 3x minus 1. Mainly because, or only because, it doesn't really make sense when you read it out loud. These are not sentences. You need the equality symbol to make this into a sentence. So this ends the video on proofs.